right, guys, so we're going to go ahead and do a quick introduction to equilibrium. This may have been mentioned in Chem 1, depending on when you took it. This is one of the units that got cut whenever we went through COVID. So you may not have had a lot of experience with equilibrium before, but we have mentioned them whenever we are looking at a reversible reaction is when we tend to deal with these the most. All right, so like I said, we tend to use these with reversible reactions. So in a reversible reaction, normally we write a reaction where the reactants are becoming products. During reversible reactions, the products that were formed can revert and change back into the original reactant. So you have a forward reaction and a reverse reaction occurring simultaneously. So the reaction can proceed in both directions. So a lot of times these are going to be represented as a double arrow. That way you can see there's a reaction going from the reactants on the left to the products on the right. There's also a reaction going from the products on the right to the reactants on the left. So anytime you see that double arrow, it kind of indicates that this is a reversible reaction. So here it just shows you we have the ammonium chloride, which is a powder, will produce the ammonia and hydrochloric acid. Those can be combined to form that ammonium chloride as well. We also look at reactions and they can be in what we refer to as dynamic equilibrium. So these are dealing with those reversible reactions that are occurring in a closed system. So a closed system might be like a flask with a stopper in it where gases and stuff cannot escape and no outside excuse me, no outside gases can interfere with the reaction itself. So dynamic equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. So we talked about the two reactions are occurring simultaneously, but they're occurring at the same rate overall. So what that means is both processes are constantly occurring, that forward and reverse reaction, and there's no overall observable change. Oops, excuse me, I hit the button twice. So even though we know the reaction's going both ways because they're occurring at the same rate, we don't actually see a difference in the amount of reactants and products that we have. So with dynamic equilibrium, the rates are the same and the amounts tend to stay the same. I'm going to show you a quick kind of simulation. What does tend to occur with equilibrium is you'll have two substances. So these two lines are representing the reactants, which are A, and the products, which are B. Notice that both of these, you will have reactants that are decreasing, products that are increasing, and then they will level off. Whenever they level off, that is when equilibrium has been reached. And it is possible that you will end up with either more reactants or more products at equilibrium, but you're still looking for when these have leveled off. But you'll be able to tell that some of these rates are the same and some of them are not. And we'll talk about some of the equilibrium graphs later on in this unit. Excuse me. But you will notice that like line A in the first graph, it goes down about 1.5 blocks. Well, line B goes up about 2.5 blocks. So B is occurring at a slightly faster rate, which is why it changes more. But we will look at those later on this unit. So this kind of ties back into kinetics a little bit for us. But remember, according to the differential rate law, we looked at what two properties of a reaction system affected reaction rate. So reaction rate was affected by the concentration and affected by that rate constant, that K value. Those are the only two things that affected rates in kinetics. So we have to look at, okay, we know concentration can change the rate, but looking at K, and if you go back looking at what affects the value of K, so the reaction rate constant was affected by the number of particle collisions that occurred and temperature and activation energy. So we said that particles had to collide. They had to have enough energy to turn into products, and temperature could make them collide more often, resulting in more products. So now looking at whenever we are talking about the value of K, that rate constant for the forward and reverse reactions in an equilibrium system. Excuse me. So with these, we can kind of look at our potential energy diagrams here. So if you talk about K, we didn't say anything about the temperature being different or the concentration, but looking at that activation energy, if you will notice, the activation energy for the forward reaction is this line. So that's 200 kilojoules is the activation energy for the forward reaction. For the reverse reaction, it is that line, which is only 150 kilojoules. So based off of knowing that they have different activation energies, it is possible that one of these is going to occur faster than the other. So that is what we can come across. So you're likely going to have different K values for the forward and reverse reaction, simply because those activation energies are different. So here, like we said, the activation energy for the forward reaction is larger than the activation energy for the reverse reaction. So what that means in terms of K is that rate constant for the forward reaction is going to be less than the rate constant for the reverse reaction, because the reverse reaction is occurring faster since it has that lower activation energy. Sorry, my mouse is going crazy. All right, so here we're just kind of looking at a quick equilibrium simulation. Here they have two containers, one representing the reactants, one representing the products, and two beakers. The beakers are going to be like representing the reaction occurring. So as we dip in the beakers, collect water, and transfer it to the other container, you'll notice that the product one, the one on the right, will start to fill up with water. But as you're transferring, some of that water gets transferred back to the reactants until the two are equal. Notice that our beakers are the same size. So because they're the same size, they end up transferring the same amount of water. So eventually they reach dynamic equilibrium, where the reaction rates are the same. We're transferring water at the same time, but notice here that the water levels are also the same. This would be different if we were using two different size beakers. So if we were using a 400 milliliter beaker and a 100 milliliter beaker, whichever one is using the 100 milliliter beaker is going to be transferring less water than the 400 milliliter beaker. So even if we're at equilibrium, we may not have the same amounts in our two at the end of the reaction when we reach equilibrium. So equilibrium doesn't necessarily mean that the amounts are the same. If it is dynamic equilibrium, the amounts are the same. It's just saying that the reaction rate, the times that we put the beaker in and transfer the water, are the same. So here is kind of a way that equilibrium can be expressed. Here we do have a graph of looking at the concentrations of our reactants and products over time. So notice here we have the dinitrogen tetroxide that is decreasing as the reaction occurs until it levels out. Our product, the nitrogen dioxide, is increasing as the reaction proceeds until it levels out. So one thing that you will notice is there's one nitrogen or dinitrogen tetroxide producing two nitrogen dioxides. So the line for nitrogen dioxide increases twice as much as the one for the dinitrogen tetroxide decreases. So you'll notice that those lines, kind of the slope of those lines, are different when they have different coefficients. Looking at the particle level down below, notice that the picture on the left, we are starting out with only dinitrogen tetroxide, which is completely clear. It's a clear gas. As the reaction starts to occur, we have some of those dinitrogen tetroxides that start to form the smaller nitrogen dioxide molecules, which is more of like an orange-brown color. Go to the picture in the middle, you have even more nitrogen dioxide, but there's still that dinitrogen tetroxide. It is an even browner color because it produced more from the second picture to the third. Now, if you compare the third picture to the fourth and the fifth, they look the same. Because if you notice, that's where the line has leveled out. We have reached equilibrium. So even though the reaction is still occurring, our amount of our reactants and products stay the same as the reaction continues. So I did kind of mention this, that the concentration of the dinitrogen tetroxide and nitrogen dioxide did not exactly change the same amount, because when we look at the rate, we're using one dinitrogen tetroxide while producing two nitrogen dioxides. The forward reaction is going half as fast as the reverse reaction is. So the reverse reaction is going to end up having a larger reaction rate because we're using more of it. So that's one reason that you notice that the two lines cross over when we're comparing concentration versus time, because we're going to be using up twice as much nitrogen dioxide. So let's look at equilibrium a little bit more. So equilibrium is when we have a reaction that proceeds in the forward direction, where reactants are becoming products, and the reverse reaction, where products are becoming reactants at equal rates. So the rates are the same in chemical equilibrium. This does not mean that the amounts have to be equal. So you can end up with more reactants or more products at equilibrium. One way that we determine which side has more of an amount is by looking at the equilibrium constant. The equilibrium constant is an expression and resulting numerical value that describes the position of equilibrium for a given reaction. So the numerical value is going to tell you, are the reactants favored in this reaction or are the products favored in this reaction? And for equilibrium constant, this is going to be represented as KEQ, and that is a capital K, whereas the rate constant from kinetics was a lowercase k. So make sure this one is capitalized. We're also going to look at K in terms of, we can calculate K using concentrations, which is that Kc. We can also calculate K using pressures if we're dealing with gases. So you may see KEQ, Kc, or Kp. They are all going to be used synonymously. Whenever we get later into this unit, we're also going to be looking at KSP. This looks at the solubility of some of our insoluble salts. And whenever we do acids and bases next unit, we are going to look at Ka and Kb. They're all going to be representatives of an equilibrium constant, but they focus on different parts of a reaction. So here we have the reaction of hydrogen and bromine is in a reversible reaction producing 2 hydrogen bromides. It tells us that the K value for this is 1.9 times 10 to the 19th. What this means is, if you notice 1.9 times 10 to the 19th, that number is greater than 1. So I'll put that here. So that's more than 1. What that means, and if you look at our particle diagrams, notice that here there is 1 hydrogen, 1 bromine, and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogen bromides. So simply counting those, notice that there are more product particles. Whenever we have more product particles or more products, our K value is going to be greater than 1. So anytime you see a K greater than 1, or it can be equal to 1, it's going to be our products are favored. So there's more products at equilibrium. All right, so let's look at this equation. Here we have nitrogen, oxygen making nitrogen monoxide, and it gives us a K value of 4.1 times 10 to the negative 31st. Notice that that is going to be less than 1. Because remember, that negative exponent is going to be a decimal number for us. So looking at our particles, when we look at the amount of nitrogens we have, there are 6 nitrogens, 4 oxygens, and only 2 nitrogen monoxides. So if you notice, there are more reactants represented here, meaning that our reactants are favored. So if our K is less than 1, it's going to be that our reactants are favored. So at equilibrium, we have more reactants, favored, more reactants than products. right, so how we find the equilibrium constant and how this ties back into kinetics. And we're going to simplify this a little bit. So here I just have a reaction. Notice that we said at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Whenever we did our rate laws in kinetics, if the rates are the same, that means that we can set them equal to one another in that reversible reaction. We did that with mechanisms. Well, if we are trying to find that K value, we have to kind of isolate the K's on the same side of the reaction. So we can kind of rearrange to isolate the K's, and notice that we end up with the product concentrations on top, the reactant concentrations on the bottom, and that is going to be equal to KEQ. So anytime we are doing a K formula, and we're going to do this a couple times, you're always going to be using the concentrations of the products on top multiplied together, divided by the concentrations of the reactants on the bottom multiplied together. And that's where you're going to get those K values from. And K does not have a unit because everything's going to end up canceling out. So we said when equilibrium favors the products, the K value is going to be greater than 1. I said greater than or equal to. That is a mistake. It needs to be greater than 1 for there to be more products. If equilibrium favors reactants, that K value is going to be less than 1. Whenever K is equal to 1, that means that we are truly at that dynamic equilibrium where the reaction rates and the amounts are the same. So K is approximately equal to 1. So if it's greater than 1, it favors products. Less than 1, it favors reactants. If it is exactly 1, we should be at that dynamic equilibrium. So how you're going to write equilibrium constants, and I did mention this a moment ago, you are going to have the products over the reactants. So notice that here we have like W plus X producing Y plus Z. So we have the concentration of Y on top times the concentration of Z on top over the concentration of W on the bottom times the concentration of X on the bottom. Notice that if these have coefficients in the balanced reaction, those coefficients become exponents for those specific concentrations. So like Y is raised to the power of C, whatever its coefficient is. If there is no coefficient, you just raise it to the power of 1 or leave it as is. If there's a coefficient of 2, that concentration needs to be squared. So make sure that products go over reactants. If you can't remember, they're alphabetical. So P comes before R. And if you have a coefficient, it must become an exponent. A note is only solutions and gases are going to appear in the equilibrium constant expression because those are the only things that have concentrations. If you have a solid or a pure liquid like water, they do not show up in the equilibrium expression. So we would just simply omit those. They don't have to be written in our equation at all. So solids and liquids you are going to ignore when finding equilibrium constants. So let's look at these and write the equilibrium constant expression for the following. So for the first reaction, we have hydrogen, nitrogen producing ammonia. We said that our products have to go on top. So on top, our product is the ammonia, NH3. And it does have a coefficient of 2, so this has to be squared. That should go over our reactants. So we have hydrogen, which has a coefficient of 3, so that should be cubed. And then we have nitrogen, which does not have an exponent, or excuse me, a coefficient, so it will not have an exponent. So that is our equilibrium constant expression. It is possible that you will come across problems that just want the expression or the formula for how equilibrium constants would be found. Let's look at the next one. This one can be kind of tricky because notice that calcium carbonate is a solid and calcium oxide is a solid. Therefore, it will not show up in our equilibrium expression. So we have our product that is not crossed out up on top, which is going to be carbon dioxide. That does not have a coefficient, so it does not have an exponent. Everything else in the equation is x'd out. So there is nothing else that goes in that equilibrium expression for this problem. All right, so let's look at how we actually calculate K. So kind of plugging in values to that equilibrium expression. So here we have hydrogen iodine producing hydrogen iodide gas, and it wants us to calculate a numerical value for KEQ if the equilibrium concentrations are as follows. So you want to make sure that you know what the equation would be first. So for KEQ, pardon me, my tablet's going crazy. So for KEQ, we have our product on top, which is the hydrogen iodide gas. That has a coefficient of 2, so it should have an exponent of 2. That is going to be divided by our reactants, which is our hydrogen. That does not have a coefficient, so it does not have an exponent, multiplied by our iodine, which does not have a coefficient, so it does not have an exponent. So we can plug in our known values and then put this in the calculator. So the hydrogen iodide is 0.78. And a common mistake is people will start plugging in numbers and forget to carry over their exponents. So make sure that you carry down those exponents as you go. That is going to be over our hydrogen, which is 0.11, times our iodine, which is 0.11. Be careful how you put this in the calculator, because since you are dividing by both reactants, you want to make sure that these bottom factors are in parentheses together. If not, it will divide by one of them and multiply by the other instead of dividing by both. So be aware of how you type that in. You can also solve for the bottom and then do the top divided by the bottom. So we have 0.78 squared divided by, make sure you open your parentheses, 0.11 times 0.11. And that gives us a K value. And I'm going to do 2 sig figs since all of my concentrations were in 2 sig figs. I have a K value of 50, excuse me. And I'm going to put decimal, so that represents 2 sig figs. You do not have a unit for K. It could also ask you what side of the reaction is favored here. Since 50 is greater than 1, here our products are favored. So you'll notice that our product concentration is higher at equilibrium than our reactant concentration. All right. And one thing that you will notice is our equilibrium constants will end up being in the same ratio with our equilibrium constant. So even when you change the concentrations, you're going to end up with the same equilibrium constant. So it is a constant, so that will remain the same given different concentrations. All right, so let's look at this one. It says at 25 degrees Celsius, our K value is 4.10. In an equilibrium mixture, the following concentrations were measured. The CH3CO2H is 0.21 molar. CH3CO2C2H5 is 0.910 molar. The hydroxide ion concentration is 0.00850 molar. And it wants to know what's the equilibrium concentration of ethanol, which is written strangely here. But the ethanol is the C2H5O is what we are looking for. So here is using the same equilibrium expression, but we're going to be solving for one of the concentrations instead of the K value. So we're going to be using the same K expression. So it should have the CH3CO2C2H5 product on top with the hydroxide on top, divided by our reactants, the CH3CO2H, and our ethanol, C2H5O. So we can plug in what we know and then solve for that unknown. So the CH3CO2C2H5 is 0.91 molar. Hydroxide is 0.00850 molar. The CH3CO2H is 0.21 molar. And we're solving for ethanol. And it told us our K value is 4.10. One thing to be careful of is ethanol is currently on the bottom. You need to get it off the bottom when you solve for it. So we do need to multiply by the ethanol on both sides. And then we end up dividing by 4.10 on both sides. And yet again, because we have two numbers that we're dividing by, we want to put those in parentheses. So when you put this in the calculator, excuse me, you're going to do 0.910 times 0.00850 divided by, open your parentheses, 0.210 times 4.10. And we get that our concentration of C2H5O is equal to, and everything is at 3 sig figs, so I'll leave it at 3 sig figs. It's going to be 0.00898. And remember, concentrations are measured as molarity. So that will have a unit.